The topic of this thesis, process parameter optimization of carbon composite production through modeling thermomechanical behavior of CFRP polymeric structure in Python. This study was developed in Gebze Technical University within the scope of master thesis. The keywords are autoclave cure simulation, springing, mold optimization, ANSYS, and helicopter blades. Before explaining the details of the solution theory put forward in this study, let's take a brief look at the historical development and production of composites and carbon fiber. The history of composite starts from the mangas bows that fit today's modern composite definition in the 1200s and passes through the first fiber-reinforced composites of Owens Corning Company in 1935. When the relevant resources are examined, it's seen that the first carbon fiber-reinforced composite was patented in 1961. Today, leading aircraft manufacturers, Airbus, Boeing, Embraer, and Lockheed Martin, are gradually increasing the percentage of thermoset and thermoplastic carbon-reinforced polymer materials used for the construction of many commercial and military aircraft. In the automotive industry, carbon fiber-reinforced composites are mainly used in the construction of the body of Formula One vehicles. The most commonly used precursor type for carbon fiber, obtained by combining more than one precursor, is PAN, polyacrylonitrile. Carbon fiber is obtained after three-step heat treatment of the PAN precursor: stabilization, carbonization, and graphitization. PAN is passed through the coagulation bath to produce precursors in the different versions such as 3K, 6K, 12K, and 24K. Toray, Beijing, SGL Carbon, Hexcel, Solvay, and Dow AXA are known as global leader carbon fiber manufacturers. According to some market forecast reports, global carbon fiber demand would increase from 58,000 in 2015 to 120,000 tons by 2022. It seems this forecast has come true. As we can see from the previous chart, carbon fiber is a precious material, and the market gives carbon fiber its due. Truth is also precious. That's why there is one truth more to give its due. The Lord created the universe and defined and drew up the fundamentals of each particle's behavior in it. In fact, the one we do as engineering is reading these routines and rules in the universe written by the Lord. As an amazing example, let's look at the inspiration of bees. Honeycomb structure. While the bees are building their honeycomb, they use two engines, and honeycomb tips are 13 degrees higher. With this great structure, honeycomb is used in many types of engineering applications. Let's look how the engineering problem is defined and what kind of engineering solution is advised in this thesis. Composite part production with non-optimized process parameters is mostly completed with certain levels of distortions. The deformed parts complicate the integration processes and cause consequences that threaten the structural health of the part. Process optimization is required to minimize threats and define tolerance values of the manufactured part. Many experimental applications are needed for process parameter optimization. Experimental applications cause high cost due to the use of autoclaves and prepregs. For this reason, it's important to examine the behavior of fiber and matrix during curing, numerical analysis of the part, and behavior modeling. CUREHAVIOUR is a prediction method provides flexible solutions, different viewpoints to process optimization, and gives opportunity to analyze the process with different aspects. You can see the aspects studied in the thesis. Process-induced distortions and stresses, integration forces, compensation methods, fatigue, lifetime and failure, and last, cure behavior modeling and scripting. While preparing this study, it has benefited from 47 sources that include theory, practice, and standards. 90% of the references belong to global authors, and more than 95% of studies published in English. In order to obtain simulation environment development, validation and experimental data, approximately 600 GB of three-dimensional solid model and analysis data were produced. In this study, warping and springing mechanisms were investigated in the production of composite parts with Hexcel AS4 UD prepreg in an autoclave environment. According to experiences and literature, there are three main active parameters that shapes the composite Q results. CTE mismatch between fiber and matrix is the first one. The second one, curing shrinkage. And tool-part interaction is the last one. As a result of these factors, process-induced distortions called spring-in, back or forward occurs in flange areas, and warpage occurs on flat surfaces. In ANSYS ACCS, the structure of Q process simulation was designed as 3 steps. The first one, designing ACP lamination and solid model accordance with orientation. Step 2, thermal Q simulation. And step 3, structural analysis. After a standard lamination, thermal Q simulation diversified into 2 models, the one mold taken into account and the one mold not taken into account, and structural analysis into 3 models. Model 1, autoclave pressure and heat. Model 2, autoclave pressure and heat conducted via mold body. And Model 3, tool-part interaction, addition to Model 2. This study is based on the Model 1 and Model 2 because of stable results and compatibility to the literature. The experimental geometry, lamination, and process cure profile were also simulated in Abacus in the literature. The results of ANSYS ACCS Q simulation, which was developed in this study, was validated by comparison with the literature results. Afterwards, in order to minimize process-based shape change, mold design optimization was made in terms of mold thickness and geometry compensation. In the validated simulation environment, the analysis of the parts with different parameter sets and different geometric dimensions were completed. The results advised how the stack up and the length change affect the deformation and stress results. As the second stage of structural health approach, the effects of integration forces on simple U-shaped part and aircraft upper shell was analyzed in terms of stress results and SIWU failure criteria. To understand the transportation conditions effects on composite lifetime, vibration responses of simple U-shaped part was analyzed under military standard test conditions. To develop a mathematical model of thermomechanical behavior on U-shaped composite part during Q, experiment design methods were performed with the combination of radius, thickness, and flange angle. Datasets obtained from this method was used to design script structure in Python. You can see the user interface of Python to predict spring angle change. In the final stage, the American Lynx ZX1790 model helicopter metal blade was modeled to composite as a case study. Cure-induced stress effects on failure results of the composite blade under a flight condition scenario were simulated in ANSYS ACCS. As a conclusion, optimization autoclave process parameters with CUREHAVIOUR approach, we can offer qualified solutions, determine design and production tolerances, increase process efficiency and reduce costs, and reduce composite structure dematch risks. With CUREHAVIOUR approach, which allows predicting the results of autoclave curing process from many different perspectives, different combinations of knitted preplex can be simulated and more comprehensive and complex mathematical models that connect different scenarios can be developed in Python environment.